Today you will be having a problem-solving session on arrays. Since you've already got the basics, today we'll build on that by solving some real problems. There will be 4 easy ones to get confident to show you the true power of arrays. For every problem, I'll explain the statement, the logic behind solving it, then walk you through a simple pseudocode. After that, I'll explain the time and space complexity in a way that will be super easy to understand. Let's get started. Problem 1. Check if a given element exists in the array. Problem statement is simple. You are given an array and a number. You have to return true if the number exists in the array. Let's see the logic to solve this problem. We go through the array and compare each element to the target number. If we find a match, we return true. If we finish the loop without a match, we return false. Pseudocode. For each element in array, if element equals target, return true, else return false. Explanation of the pseudocode is simple. We just compare elements one by one. The moment we find a match, we return true. If we don't find the number after checking all elements, we return false. Let's dry run with a test case. Input array equals 10, 20, 30, 40. Target equals 30. Compare 10 equals 30, which is not equal. Now compare 20 equals 30, which is not equal. Compare 30 equals 30, which is yes, so return true. Output, true. Input, array equals 1, 2, 3. Target equals 5. Compare all. Since we don't find a match, so no match. So, output is false, which means the element doesn't exist in this array. Let's see the time complexity. Look at the pseudocode once again. In the worst case, we might have to check all elements if the target is at the end or not present. So, time complexity is O(n). Space complexity. Again, no extra storage used, just comparisons. So space complexity is O(1). That means even if your array grows, your memory usage doesn't. It's efficient in terms of space. Problem 2. Calculate the sum of all elements. Problem statement. Given an array, return the sum of all the numbers. Let's see the logic. What we are doing is basically we just keep a variable sum and adding each element to it as we go through the array. Let's see the pseudocode. Set sum equals 0. For each element in array, sum equals sum plus element. Return sum. We initialize the sum as 0. Then for each number in the array, we just add it to the sum. At the end of the loop, the sum will contain the total. Let's dry run with a test case. Input 5, 1, 3, 2. Start. Sum equals 0. Add 5, so sum equals 5. Now add 1, so sum gets updated to 6. Add 3, so sum equals 9. Add 2, so final sum equals 11. Output is 11. Now let's talk about time complexity. We are going through the array one element at a time. So for n elements, it takes n steps O(n). Space complexity. We were only using one variable sum and not storing anything extra O(1). Constant space. Think of it like you were using just a notepad to keep track of the total. Doesn't matter how long the list is, you were using only one small space. Problem 3. Count even numbers in an array. Problem statement. Given an array, count how many elements are even. Logic for solving this is simple. We will simply check each number. If it is divisible by 2, we increase our counter, and at last, we will print the count of it. Let's have a look on pseudocode. Set count equals 0. For each element in array, if element modulo 2 equals 0, count equals count plus 1. Return count. What we are showing is basically we start with a counter set to 0. For every number, we check if it's even using the modulo operator. If it is, we increase our counter by 1. Finally, we return the count. Let's dry run with a test case. Input 2, 5, 6, 7, 8. Start. Count equals 0. 2 modulo 2 equals 0. So, count equals 1. 5 modulo 2 not equals 0. So, no change. 6 modulo 2 equals 0. So, count equals 2. 7 modulo 2 not equals 0. So, no change. 8 modulo 2 equals 0. So, count equals 3. Output is 3. Time complexity. Since we are checking each number once, so time complexity is O(n). Space complexity. We are only using one variable count, so space complexity is O(1). Even if the array grows from 10 to 1 million elements, we're still just using one counter, so no extra memory is being used. Problem 4. Find the maximum element in an array. Let's understand the problem statement. You're given an array of numbers. Find the largest number from the array. Let's see the logic to solve. We will start by assuming the first element is the largest. Then we compare every other element to it. If we find a bigger number, we update our max. Let's have a look on pseudocode. Set max equals first element of array. For each element in array starting from second, if element is greater than max, set max equals element. Return max. We begin by setting max as the first number. Then, one by one, we look at all the other numbers. If we find any number greater than max, we update max. At the end, max will hold the largest value. Let's dry run with a test case. Input 3, 7, 2, 9, 4. Start. Max equals 3. Compare 7 greater than 3, which is true, so max equals 7. Compare 2 greater than 7, which is false, so no change. Compare 9 is greater than 7, which is true, so max equals 9. Compare 4 is greater than 9, which is false, so no change. Output is 9. Now let's talk about time and space complexity. We go through each number in the array once, from start to end. So if the array has 10 elements, we do 10 comparisons. That's why time complexity is O(n), where n is the number of elements. And since we are not using any extra data structures, just one variable called max. No matter how big the array is, we were only using constant space, so space complexity is O(1). So today we have explored 4 array problems, covering everything from finding values, summing them, checking conditions, all using just a single pass and constant space.